Hello, can you guys hear me?
Yes, yes.
Okay, so hello everyone. So my name is Achinkya, and so what we'll do today is a problem session on week 8 course material on graph theory. So for those of you who are new, so here is how this session will go. So I'll give you a problem and I'll give you some time to think about it. And once everyone is done, we'll discuss your ideas and eventually we'll see the solution of the problem. Okay. So I think, as far as I remember, there are three concepts covered in week 8 which are new. So first is chromatic index. So last time we saw chromatic number, which is the least number of colors required to color the graph. I mean, I'm talking about vertex coloring. And then now we saw edge coloring, and the minimum number of colors required to color the edges, such that no edge is monochromatic, or the end. I mean, so that's called chromatic index, which we will see. And then what we have one more concept is on planar graphs. So this is a new kind of a graph where you can draw it on a plane so that the edges don't overlap with each other, so they cannot cross each other. And if there is such a drawing of a graph, then we call it a planar graph. Okay, so we'll start with, I think, chromatic number and chromatic index problems, and then simultaneously we'll see some planar graph problems as well. Okay, so let me give you a problem. So okay, so let me write it down and you can start thinking about it. So okay, so okay, so here is a graph G. So let me just write down the name of vertices. So what you have to do is you have to determine the chromatic number of G. Okay, so those of you who know chromatic number is, you can start thinking about it. If there is anyone who doesn't know what a chromatic number is, you can write it in the chat and I will explain. And if all of you know, then please start thinking about it. And yeah. Okay, so like I said, if there is anyone who doesn't know what a chromatic number is, please ask. Okay, so don't be, yeah. So once you have solved the answer question, please write the answer in the chat, and then we'll see if it is correct, right? So okay, yeah, I see only one answer. I'll give you a minute extra minute to think about it. Okay. Okay, I think I see a lot of answers. Okay, so okay, half of you are saying it is 3, half of you are saying it is 4. Uh, and okay, I think there's one more 4. So okay, let's see. Um, it is at least 3, that is for sure, because clearly we have a cycle. So if you ignore the vertex G here, so if you ignore the vertex G, we have a C9, cycle of length 9. And we know that if you have a odd cycle in a graph G, by odd cycle I mean any cycle whose length is odd, you will always need at least 3 colors. Now the question is, can you do it in 3 colors or do you need 4, right? So let's start by trying for 3 colors, and if we succeed then the answer is clearly 3, because like I said, the answer is at least 3. And if we could not do it, then we'll see if there's some problem. Okay, so okay, so let's start by coloring the cycle, so the surrounding cycle. So let's say okay, so let's say I color it this one red, and then I'll go alternate. So red blue like this. So red, blue, red, blue, um, then again red, then blue, red, blue. Okay. Now, is this much correct? So I don't see any edge between. Oh, okay, there's a problem. I added an edge between two vertices which are colored blue. So this. Okay. So can you see this is not a correct coloring? Can anyone tell me why? Is there any problem with this much coloring? Um,
I
So
and
I and
yes, I
C.
and C is clearly. So I need to put two different colors for I and C. Okay. So okay, so let me put green color here. Uh, and then let me put green color here also. So now is there a problem with this much part? Uh, I don't see a problem, right? So green, red, green, blue, blue, red, and then if I put green here, then is there a problem? So AB edge is fine. So the outer cycle is correct, fine, because I have used 3 colors, and clearly two adjacent vertices are getting two distinct colors. Now the only question we have to ask is if these edges which are extra inside this cycle, are they making a problem? So BJ edge is clearly fine because green and red. CI is fine because blue and green. DE is fine because blue and red. And then finally, let's look at the vertex G. GA is fine, GH is fine, GF is fine, right? Because green, red, and green, blue. Uh, is it correct? Or do we need one more color?
It is correct, sir. It is correct.
Let me see. It's okay. I think a lot of you said 4, so that's why I'm just making sure. Yes, so this is fine. So here we need so so okay. So let me write a little bit. So since since the graph contains a cycle of length 9, which is odd, we will need at least 3 colors. We will need chi of G to be at least 3. So I'm denoting the chromatic number by chi of G. And since there's an odd cycle, this is at least 3. And we have colored the graph with 3 colors. Graph with three colors. Therefore, it implies that chi of g is equal to 3. Okay. So if this is clear, put +1 in the chat. If not, please ask me questions.
Sir, is there any relation between chromatic number and H coloring chi dash G?
Uh, I mean, there are some inequalities, but there is no direct relation. I mean, I don't think there is any general relation between chi of g and chi prime of g. So yeah, no, I don't think there is any relation as far as I know. It is not there in the course, that I'm sure, because I have seen the lectures and I didn't see any relation. So most likely no. Okay, let me see. Okay, I see.
Just like we did this vertex coloring can be same with, we can see edge coloring also in the same problem.
Wait,
Can we try?
I didn't understand. So what can
So
we
can
do?
we try edge coloring in the same graph? Then we can see.
Okay, sure. So let's take the same graph. Okay, I think I over. Okay, so let me color it black again. Okay, anyways, so let me color it black actually, and let's try to find the chromatic index of the graph. Okay, so chromatic index is you have to color the edges so that no two adjacent edges have I mean, yeah. So to no two adjacent edges have same color, right? So okay. So the question is, so let me write, and also what is the chromatic index? Okay, so let me also think. So you guys can also start thinking about it. So if there is anyone who doesn't know what is a chromatic index, please ask. And if all of you know, then start thinking. Okay, so once you get an answer, please write it in the chat. So we'll see if that is correct, right? Anyone? I don't see any answers yet. Okay. Um, okay, so he's saying the answer is 4. Is there anyone who has colored the edges with only 3 colors? Okay, I see one more 4. So, okay. So let's see together. So let me just take this. bigger down and we'll color the edges. Okay, so there's a I I think wait. Do you see what I'm writing? I think there is some delay probably on the screen sharing. So can you see what I have written here or
No,
not?
sir. Screen is not visible. Screen is not.
Okay, okay. Let me wait. I think there's some problem. Let me just okay. Let me just reconnect. Okay, just wait a minute. Uh, okay, I think let me see. Ah, okay. I think it is okay now. Okay. So what we have to check if the answer is 4. So the first theorem that you must know when it comes to chromatic index is the following. So I'm denoting the chromatic index using this notation called chi prime of g. So chi of g is chromatic number and chi prime of g is chromatic index. Okay. So this is either equal to delta g or this is equal to delta g plus 1. So for every graph, okay, for every graph you will see the chromatic index is either delta g or delta g plus 1. So this is a theorem. I think it is mentioned in the one of the lectures. Okay, so you can check that. But so we just have to determine if the answer is delta g or delta g plus 1. So what is delta g in this graph? Can anyone tell me what is delta g?
Delta G is sir,
Hmm.
3, sir. 3, 3.
Let's see, 3. Yes, so delta g is 3. So you are right. So let's see. So we have to check whether we can color it in using 3 colors or do we need 4. Okay. So let's start by coloring the edges. So let's start with the outer cycle. So clearly we need 3 colors again, right? Because like I said, if there's an odd cycle, you will need 3 colors for each coloring as well. So if you do it like this, red, blue, let's say red, and then blue, then red, then blue, then again red, then blue, and then eventually you have green. Okay. Um, okay, this is correct, right? So for till now there is no problem. So now let's see if we can use only these 3 colors and make the graph. I mean, color all the edges. So I think the problem will happen here when we are coloring the edge CI. So for example, I cannot use the color red or green or blue for the edge CI because clearly uh, there are 2 edges adjacent to C, CA and CE. One is colored blue, one is colored green. And for I, one is blue and one is red, right? So here. So clearly, at least with this coloring we cannot make it 3. So let me just think if we can do something. uh, so what if let me just see, let me just try this. So instead of turning this into green, I'll make this green and then I will make this red. Okay, now I can color CI with green. right? So this is fine. Uh, oh, now the problem is with the age bj now. Similarly, uh, okay, okay. So let me do this. Mm, green. Okay, so let's see. So can anyone try to figure out why do we need, why we will need at least four colors here in this case? Is it true that we will need four colors, or we are not able to find three coloring, right? So there are two possibilities. It is not there, or the other possibility that we have to consider is that we are not able to find it. So can anyone argue why we need at least four colors in this case?
If we color Hg by green,
Hmm.
then you cannot color Ag by any one of the three colors.
If I color HG green, GA I can color blue, right? So if I color HG as green, oh sorry, green, I can make this as blue. But the problem right now is with, as far as I think, with the age BJ, because even DE can be colored with green, right? But now with BJ, I cannot color it red, blue, or green because the HDB and BA are colored blue and green, so it should be red. But I cannot even color it red because IJ is red. And at the same time, the GF age is also problematic. I cannot use any of these three colors, so I must color it with uh, what do you call it? New color. So I'll need, let's say, let me just use purple. Let's get this. Okay, so four is definitely possible, and I don't think three is possible. Um, so is there anyone who got 3H coloring? No, right?
So this is a planar and simple graph, so we can try a trial and error method.
Wait,
But
this is not a planar. Is it a planar graph? What do you think?
this is, I think, is a planar and simple graph. They're not complex, wherein the edges and that vertices are more. But
No, wait,
the
wait, wait.
point is,
This is
Simple is
not planar.
so this doesn't look planar. I have clearly drawn edges which are overlapping with each other. So the graph is not planar. By simple, you mean there are not too many edges or too many vertices. I think.
no, that is what I want to say, sir. Now we can try this, as you said, we can try this by purple and we are getting the result. But
Hmm.
the problem is if it is more then it is very trial and error may be wrong.
Yes, yes, yes.
So
I
then
agree.
how to resolve that?
No, so th- see, you need, if you have lot of vertices and lot of edges, there is no fixed theorem or anything. So for example, for planar graphs, there is a theorem which says that every planar graph can be colored with four colors. So this is given in your course lectures, but I don't think this graph is planar because clearly, I mean, it could be planar in the sense that, so for example, so let me just say this, I
Sir,
think this
this is
will,
planar. This is planar graph. I will prove you why. Because you extend this internal thing to outside, so this will become as a planar graph. So
okay,
now if you pull G and keep it out, and then the B and I and C and B and J and C and I you can pull it out. It will be planar.
okay, let me see.
So C and I you can pull it. It will come out. Similarly,
No,
B
actually,
and J
this,
will.
no, so actually, so you'll see. So my second question is basically the same, that is this graph planar, right? And I shouldn't, okay, I shouldn't answer immediately, but the answer is no. This graph is in fact not planar. You can try to draw, what you are saying is keep G outside this this C9 cycle and draw the graph again. and you might have a planar drawing which basically in such a way that these edges don't overlap with each other. But we can prove that this graph is not planar, and I will do it in a minute. But let me just say that this graph is not planar, okay? And we will prove it. uh,
we can convert it into K file.
wait. Let's wait. We have to go step by step.
Okay,
So first
okay.
of all, I think this is uh, definitely four colorable. I don't think this is three colorable. We'll get to planar part. Don't I mean, let everyone think. I'll get to the planar part and I'll ask you the same question, and then we'll discuss that. Okay. Right now, just hold on for a minute. Okay. So this is definitely chi. So for chi prime of g, the answer is delta g or delta g plus one. If the graph is simple, you can always try with coloring, different colorings. There is no one specific method that says that if you do this, then you'll get the answer. Okay. So you will have to do trial and error. Okay. Four definitely possible. Three or four is the answer, and four is 100% sure. And as far as I see, there is no three coloring, so I think the answer is four. Okay. So let me give you one more question. Let's go step by step. We'll come to this chromatic index one more time, and we'll see this. Okay. So let me give you one more graph, and I'll ask you the question. Uh, okay. So let's say. Okay, so let me first ask you, uh, why is okay? So I said that chi prime of
Sir, your
g.
screen is again not visible. Okay, now it is visible.
Okay, I think there is some internet issue, but let me just okay, write down this. So this is, just wait. I think it will appear. Yes. So we know that chi prime of g is equal to delta g or delta g plus one. Can anyone tell me why uh, chi prime of g is always greater than or equal to delta g? Why can't it be less than um, delta g? Why is this true? So for any graph g, this is always true. Chi prime of g is always greater than or equal to delta of g.
Because of adjacent edges.
Adjacent edges, as in, can you elaborate a little bit?
If a vertex has uh, maximum degree delta of g,
Okay. Yes, you're right. So if you take a vertex, so I know that maximum degree of the graph is delta g, which means that there is a vertex whose adjacent to delta g many edges. So let's say this vertex is u. So let's say this vertex is u, and let's say these are the edges coming out of it. So let's say this is u1, u2, u3, dot dot dot, u up to delta g. So the simple observation suggests that since u is common vertex to all these edges must be colored with distinct color, right? So if I use red color here like this, clearly I cannot color u2 with the red color. So I need to use some different color. So let's say I use blue. Now when I'm coloring u3, then clearly I cannot use red or blue because of the first two edges. So the answer is, I mean, so the observation is that chi prime of g is always greater than or equal to delta g, right? And now there's a theorem which is given in the class without proof by, I think, Vizag, which is in some 19th or 20th century. He proved that chi prime of g is at most delta g plus 1. Okay. So you can keep it in mind that whenever you are asked to determine um, the chromatic index of a graph, you just have to determine whether it is delta g or delta g plus 1. Okay. So the answer is always one of these two. When it comes to chromatic number, is this true? If Is it true that a graph can have a maximum degree 100, but chromatic number can be very low, I mean less than 100? Is it possible? So let me write down. So I think, so I'm just asking these questions to make sure that the difference between chromatic number and index will become very clear. Okay, so my question is that, is there a graph with maximum degree 100, but the chromatic number Let's say it's just 2.
Sir, the question is not visible. What
Okay,
you
it
are
will just a second. I think it will appear. I think there's some. Oh, okay. Is it visible now?
says.
Okay. So just be patient for some time. I think there is some internet issue, so I can't do anything about it for now. Okay, so I think now it is visible. So the question is that, is there a graph with maximum degree 100, but the chromatic number of that graph is just 2, right? So you can think for a minute if such a graph can exist, right?
Yes, sir.
Okay, so wait, let everyone think. Vertex or edge. Okay, wait, let me see. There's a question in the chat. Vertex or edge, sir? Planar graph for colorable. It is vertex coloring. So yeah, so planar graph is, when I say it is four colorable, I mean vertex colorable. Whenever we say four colorable, three colorable, we mean vertex coloring. And if we are mentioning that three edge colorable, two edge colorable, then I'm talking about edge coloring, right? So this is a theorem that says that planar graph is always four colorable. Okay. Now my question is this: so is there a graph with maximum degree 100, but the chromatic number of such a graph is 2? Can such a graph exist? If you think this is possible, put +1. If you think this is not possible, put -1. Okay, so I think most of you got it. So yes, you are right. So okay, so I think somebody saying the answer is to this question is star graph. Yes, so this is also true. So if you take a star graph like this, and you take a vertex u which is adjacent to, let's say, 100 vertices, you can color this one as, let's say, blue, and you can color all of these as red because there is no edge between them, right? So that's why I think there is no any good relation between chromatic number and chromatic index. Chromatic number can be very small compared to the maximum degree, but chromatic index can be either delta g or delta g plus 1, right? So if I replace this statement with index, then the answer is no. Why? Because the maximum degree is 100. So the answer of chromatic index should be 100 or 101, right? So if I replace chromatic number by chromatic index, the answer is no. Okay. Okay. So let's go to the next question. Uh, okay, just a minute. Let me write. Okay, so let's do one more question. It is question 4. So consider the graph given below. Calculate the chromatic index of G. Okay, so let me draw the graph. So this is a bit. Yes. Okay. So here is a graph G. Wait, sir, say about chromatic number bound. Is there any? Um. So for chromatic number, the bound is, I think, delta G plus 1. So there is only an upper bound. I don't know if there is any lower bound. I don't think there is any lower bound. So yeah, so let me write here. So what we see said is that chi prime of G is always greater than or equal to delta G and at most delta G plus 1. Similarly, the chi of G is also at most delta G plus 1. So this is a theorem which is proved in class. So this is proved in class, right? So this is the only bound that is done in class, which is an upper bound on chromatic number. Okay. Uh, okay. So here's a question. I think again there's some delay. Just a second. Wait. Just a minute. Some problem. Okay. Okay. So this is visible now, right now. This graph and what I wrote above.
Yes, yes,
Yes.
yes, yes.
Yeah. So I think there is some problem, but it's okay. So this chi of G is at most delta G plus 1, right? So this is a theorem that is proved in class. So here is a new question, question 4.
Again, yes, yes.
Yeah. So here you have given a graph G and you have to determine the chromatic index of G, which is the least number of colors required to color the edges of this graph. Okay. So you can think. Wait. Okay. I think this is okay now. So if you have solved the question, please don't write the answer immediately. I'll tell you to write it down after a couple of minutes because others will also try on their own. So let them also think. Okay, so if anyone has chromatic index, you can write it in the chat. Um, okay. Okay, so some of you are saying it is 4. So I see the maximum degree is 3. So the answer is definitely 3 or 4. Uh, so okay, so I think everybody's saying 4. Uh, okay, so is if okay, if there is anyone who has colored the edges with only 3 colors, put +1, right? Otherwise, we'll see if we can do it with 3 and then we'll see it 4. Okay, I don't see any +1s, so I'm assuming everybody did with 4 colors. But I think the answer is 3. So I think, so let me show you the coloring and then you will see that this is in fact possible. Let me, this as red, uh, this as blue. Let me take this with 3, so green, and then again red, then let's say blue, and then green. Okay, so right now there is no problem yet. Okay, so let's see. So now I have to do this red. I have to do this one also red, because red, the complement blue and green is already there. So for this one I need blue. For this one I surely need blue. Then for here I need green. I need green for sure. Okay. Again I need, let's say here, green. There is no problem because the other endpoint is adjacent to red and this one is colored adjacent to blue, so that edge is should be colored green. Okay. Okay, now it's visible. Then I'll do it red here. Then I need to do blue here. Then I need to do uh, green here, and then I need to do blue here. Okay. So okay, so here is a wait. There is one edge left, which should be colored red. Okay. So in fact, three colors are possible. Okay. So the answer to this question is three. So like I said, phi prime of g is equal to 3. So when you see a problem, please take your time, because this kind of mistakes can happen. You might, because the answer is definitely less than or equal to 4. So the interesting part is, can you do it with 3? So in this case it is possible. So okay, so can you calculate the chromatic number of the same graph, right? So the same graph, chromatic index is 3. What about chi of g, right? So so let me just color it black again. So let me just cut paste this. So let's take the same graph. Let me color it black. So here is a graph, the same graph I'm giving you, and my question is, what is the chromatic number? Okay, so let's say black, black. Okay, so I think this is fine for now. So you can try and calculate the chromatic number. Okay, so this time please take your time and see if you can do it with less number of colors.
Sir, actually, in the previous edge coloring problem, sir,
Hmm.
when we color all the cycles by the only by two colors, then it is impossible to find within two colors, three colors. We couldn't do other
Yeah,
things.
yeah, yeah. I also started feeling the same thing once I saw this example. So,
Uh,
for
so,
now,
how to identify the critical part of it? See, if I color the outer range by outer range first, then going into the inner part, then it's not coming now, sir.
yeah, that is true. That is true. In fact, let me just see once again here if we can. So this purple can can it be turned it into something else? So if I make this green, so for example, let's say, then I can wait just a second. So this was colored red before. Red, red. Okay, I'll do this at the end. I'll let me just first do the questions on every concept, because otherwise we'll get stuck there only. So this is, I mean, a trial and error question. So this is a matter of spending time on it and seeing it, and try to see if we can also prove a lower bound. Okay. So don't worry about it for now. Let's just focus on this one for now and see if you can find a chromatic number of this graph. Okay. We'll come back to it once we see the questions on every concept, right? So the question is, what is the chromatic number of this graph? I hope you can see the graph. Let me just reconnect. I think there's some problem with the internet today. Okay, I think it is visible now. Okay, so for now, let's just focus on this one, right? Let's see some chat. Triangle, three colors, one hint. Okay, so let's see. So I think the answer is three. You guys are correct. So clearly the answer is at least three because we have two triangles here. So if you see, let me just color for now. So for example, this is a triangle, right? So this is a triangle. So you clearly need at least three colors, right? So let's see if we can do it with exactly three colors. So the answer will be exactly three, right? So we can, let's do one, two, three, one, two, three. Okay. Yes, so I think this is possible. So you can do one, two, three, and one, two, three. Right. So this is three, two, one. Right. So this is possible. So here is a chromatic number, or sorry, vertex coloring with only three colors. So the number is basically showing the C1, C2, C3 color. Okay. So this is possible with three colors. So in this case, chi of G is also three. So it implies that chi of G is actually, sorry, equal to 3, right? Because we did it with three colors and we also proved that at least three are required. Okay. Okay. So let me give you the next problem. I think it is stuck again. So sorry. I think this is wrong. Question: if G is a cubic Hamiltonian graph, Hamiltonian graph, then phi prime of G is equal to what? Okay, so okay, I think it's visible. So here is a question. So I think this is relatively interesting and also a little bit hard to see, but let's see if you can solve it. So the question is that G is a cubic graph and also Hamiltonian graph. Cubic means that every vertex has degree 3, right? So this is means cubic. And a Hamiltonian graph, I think you already know. Any graph which contains a Hamiltonian cycle is a Hamiltonian graph, right? So a graph is cubic and Hamiltonian. And the question is, what is the chromatic index of such a graph? Right. So I think this will require relatively more time. So I'll give you 2-3 minutes to think about it. Okay. Uh, what is cubic Hamiltonian graph? Okay, so let me first say what is cubic. So a graph is cubic if every if every vertex has what's wrong with this? Vertex has degree equal to 3, and a graph is Hamiltonian if it contains a Hamiltonian cycle. Uh, I hope all of you remember what is a Hamiltonian cycle. If you don't remember, please ask. Right. So now here the graph is both cubic and Hamiltonian, which means that every vertex in the graph G has degree exactly 3, and we also know that this graph contains a Hamiltonian cycle. Okay. Okay. So if you have any questions, please. Okay. So somebody says 3. Okay, so let me give you some more time for others. Take a couple of more minutes and think. Uh, um, okay, so so how many of you think it is 3? Put +1, and those of you who think it is 4, let's put -1. Let's see, because the answer is either 3 or 4, right? Because of what theorem we have seen. Chi prime of G is either 3 or 4, because the maximum degree here is 3, because every vertex in my graph has degree 3. So so the answer is 3 or 4. So if you think the answer is 3, put +1. If you think the answer is 4, put -1. I still don't see many answers, so I'll give you one more minute and then we'll come back. Oh, okay, I see now. Okay, so can you tell me why is it 3? Why do you think it is 3 and not 4? uh any one of you?
Is there is a it is a Hamiltonian graph. Therefore, if we will always find a cycle which will contain every vertex, right?
Yes.
So like if there is a cycle, it would be either an even cycle or an odd cycle.
Mm-hmm.
If it is even, then there are like two colors which we are going to require
Yes.
to cover it. And now every vertex, because every vertex is covered, it will be related to one more vertex. Either that vertex will be some other vertex entirely,
Mm-hmm.
or it will be related to the vert it would be related to the vertex in the cycle. Now, because we have used two colors, we can always join them by another third color. Now, the vertex we are joining it with has is also being used up because it is also connected in a cycle.
Mm-hmm.
Therefore, any vertex between those two would
Mm-hmm.
make sure that those two vertex will not be used up.
Okay.
So that is for the even case. Now, if we move on for the odd one,
Mm-hmm.
now again we have the cycle.
Mm-hmm.
Now, again, that similar thing is extended. Uh, that similar logic will be extended
No, so
or
for example, I think there could be a problem, like you saying, if there's an odd case, it could be this situation. So let's say this is
Sir,
cycle. Wait. I think I probably know what you are going to say, but let me just explain it to him. So if this is the case and this is the edge that is left covered, so let's say this is a cycle, and like I said, if there's an odd cycle, you have colored, you use three colors. So let's say one, two, this is 2 again, and 3. So if you have used 3 colors and the third degree or the third uh, edge that is addition to this vertex is like this, then you are in a trouble, right? Because you cannot use any of these 3 colors and you might need 4. Okay, so in the
uh,
even case you are right. In the odd case you could uh, I mean you could come across such a uh, problem. So what will you do here?
uh, can you please explain it to me again? I
Okay,
didn't.
so what you're saying is there is a Hamiltonian cycle, right?
Yes.
There are two cases: either it is of even length or odd length. Okay, so let's say take case one. If it is a odd length cycle, which is Hamiltonian, and let's say this is a Hamiltonian cycle, it goes like this and goes like this. Okay, so let's say there is no edge here. So let's say the cycle goes like this here, and we know that every odd cycle can be colored with 3 colors. So let's say I'm coloring the edges with 3 colors of that cycle. So let's say I come across edge UVW, and let's say ABC, and like I said, I'm coloring the edges of this Hamiltonian cycle with 3 colors, right? So I use, let's say, UV as red, VW as blue, AB as green, and BC as blue. Like I said, I'm using 3 colors. So I have used only 3 colors here for the Hamiltonian cycle. Now the question is, every vertex has 3 degrees. So clearly B has two neighbors A and C. So there is one more neighbor B must have. So let's say what if B is sorry B is adjacent to the vertex V. Now the problem is that for the edge BV, you cannot use any of these 3 colors, right? Because you cannot use green and blue because this ABC, and you cannot use red and blue because UVW. So so clearly, if you have a odd length cycle, odd length Hamiltonian cycle, then you are in trouble because of such cases. Now, but before going into the odd length Hamiltonian cycle, let me take a step back and ask you, um, the so the length of the Hamiltonian cycle is the length of vertices. Sorry, total number of vertices, right? So if there are 4 vertices, then the length of Hamiltonian cycle would be 4. If there are 5, then the Hamiltonian cycle would be of length 5. So now the question is it possible that the graph contains odd number of vertices? This is the first question you should ask yourself.
no, no, no.
No, right? So the case 2 in your explanation is actually not required, because there cannot be odd number of vertices. Now can you guess why there can't be odd number of vertices in this graph, G? So for the others the question is clear, right? So what I'm asking is, so this is this so we have given that G is a cubic Hamiltonian graph, and my question is, can a cubic Hamiltonian graph contain odd number of vertices? Is it possible? If you think it is yes, can you give an example? If you think no, why do you think it is no? Take a minute and think.
In the previous session,
uh,
Hamiltonian will have only even number of vertices.
no, no, so let me give you an example. So here is a graph. So let's say it contains five vertices, and so this is a Hamiltonian cycle of length 5, because 1, 2, 3, 4, 5. So Hamiltonian cycle can have odd length. So this is possible. So what else you can say here?
Sir, if we take K4, is it a cubic Hamiltonian graph? K4.
Okay, so let's say you take K4, then you see a Hamilton. Yes, so this is a cubic Hamiltonian graph, but it contains even number of vertices, right? So one, two, three, four. My question is odd number of vertices. Is it possible that there is a cubic Hamiltonian graph which contains odd number of vertices?
So if we add one vertices in the K4, then attaching three
Add
edges, it
twice the
cannot be
number of
cubic.
vectors.
Yes.
Wait, I couldn't understand. Can talk?
So if we add one vertex and we
Twice the
cannot
number
have
of
a.
edges, summation of degree.
Yes, so she is right. So sorry. See, the problem is the following. Uh, do you remember handshaking lemma? So
Sum of all the
yeah,
degrees is equal to
so the
twice.
handshaking lemma, yes. So she's right. So the handshaking lemma from the first class says that sum of degrees must be even. Sum of degrees. So if you take all the vertices and add all the degree of every vertex, the answer should be even. Now I know that every vertex has degree 3, right? So this is basically like this. So degree of v, sorry. So this is just 3, and this is v belongs to v of g is equal to even. So this can be written as 3 into mod v of g is equal to even, right? Because I'm adding 3 how many times? N times here, which is number of vertices. Now, when is this possible? So 3 into n is even. Can n be odd?
No.
No,
No.
right? Because odd into odd
No.
is
Mm.
equal to odd. So you must have
Yes.
n as even. So in your case, your explanation was correct, but second case is not required, right? So we don't, I mean, it cannot be the case that a graph is cubic and at the same time it contains uh, odd number of vertices. So what we can say, okay, let me write down everything here, what I just said. So, so what I'm saying is this, uh, as G is 3 regular. So this is again another way to say the graph is cubic, right? 3 regular means every vertex has degree 3. Graph by handshaking lemma, G has even number of vertices. Okay, so this is the first observation of this problem, that there are even number of vertices. Now the second is that there is a Hamiltonian cycle. So let's call it C. So let's say C be a Hamiltonian cycle. Okay. Now, uh, so let's first try to color the edges which are on this Hamiltonian cycle. So how many colors do we need to color this Hamiltonian cycle?
Two colors, since number of vertices is even.
Yeah, since the cycle length is even, we need only two colors, like the alternate edges, right? You take the first one red, then blue, red, blue, red, blue, red, blue, like this. So color the edges. So you color the edges of C with two colors. Now, so we have used two colors, and how many edges do we have colored? So can anyone tell me how many edges? So what is E of G? How many edges are there? And okay, so how many edges are there in this graph? Can anyone tell me in terms of V of G? So if there are n vertices, how many edges are there?
3n.
Uh, is it 3n or something else? Is it 3n? Think again.
No, 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 no.
n plus 1 by 2.
No, n into n plus 1 by 2. So if a graph is complete, then it is in fact n into n minus 1 by 2. It is never there. There is no graph with n vertices with n into n plus 1 by 2 edges, right? Uh, 2n plus 1. No, this is also not true. Wait, you should be able to answer this question because this is very simple. So, do you remember if there is any relation between the degree of vertices and the number of edges? Is there any such relation that you have learned before which relates the number of edges and the degree of vertices?
Sum of degree is equal to twice and edges.
Exactly. So this is the handshaking lemma, right? So the sum of degree of vertices of all the vertices in G is equal to EG. So the degree of every vertex is 3. So this is equal to 3 into mod V of G. Oh, sorry, this is 2. Wait. Uh, so 2 into E is equal to sum of degrees of vertices. And this is equal to 3V of G. Now E of G is equal to 3 into V of G divided by 2. Okay. So there are these many edges in my graph G. Okay. Now, how many edges are there in my Hamiltonian cycle? Right. So my question is that
Yeah.
there are total 3 into V of G by 2 many edges, out of which I have colored the edges on the I have colored the edges which which appear on the Hamiltonian cycle. So how many edges we have colored till now, and how many are left?
We have colored mod B of G.
Yeah. So I mean, if there is a cycle with n vertices, then there are n edges, right?
Hmm.
So, so what we can say is that uh,
With two colors, we have colored mod B of G.
yes, yes.
Mod
So
B of G edges.
yes, yes. So how many are left? Basically, V of G by 2, right? So there are total 3 into V of G by 2 edges, out of which we have colored uh, V of G many edges, right? Now we have only one color left, and we have V of G by 2 many edges left, right? Because if you subtract 3 into n by 2 minus n, you get n by 2, right? Yes. So you are left with n by 2 edges, and uh, we have colored n many edges. Okay, so now let me ask you this question. So let's say this was the cycle, right? So these were the vertices, and then there were few more edges coming out of the vertices. But so let's say something like this. So this, something like this. Now let's look at the graph. So I had this graph G, which is cubic and Hamiltonian, right? How would this graph look like if I delete the edges on the edges that appear on the Hamiltonian cycle, right? So what I'm asking is, so this is my graph G. If I delete all the edges that appear on my Hamiltonian cycle, so these are edges of Hamiltonian cycle. So this is my new graph, which is G minus E of C. So my question is, how would this graph look like? G minus E of C. Can you see? I mean, can you guess? Or, I mean, can you conclude something from there?
We have to delete all the edges.
No, no, no. Wait. I'm saying you had this graph G. You are only deleting the edges that appear on the cycle, Hamiltonian cycle, right? So there were total 3 n by 2 edges, out of
So,
which I'm deleting n edges. So I'm left with n by 2 edges. So how would this graph look like?
okay. Actually, with every vertex, one more edge will be there. So we can color the other edge by another color.
No, no, but that is, I mean, yeah. So you are,
Because every vertex is adjacent to two vertices.
hmm.
So
Yes,
since
yes. So you are right. So let me just say what she said, but a little bit more formally. So this graph G of E minus C is a one regular spanning graph. So let me say what is this exactly. Okay, so let's see. So what you are doing is this. So there was a cycle, which is a Hamiltonian cycle. Um, so every vertex appears on the Hamiltonian cycle by definition. Okay, every vertex have two edges adjacent to it on that cycle, right? So if you look at the cycle, how would look like? It would look like something like this. And if you take a fixed vertex, so let's take red vertex, then it is adjacent to two edges. So let's say this purple edge and this purple edge. So every vertex is adjacent to two edges in the Hamiltonian cycle. Now I'm saying, what if I delete the edges that appear in the Hamiltonian cycle? What is the degree of every vertex? Can anyone tell me what is the degree of every vertex once I delete all the edges which appear in Hamiltonian cycle? Uh, yes,
One.
one, right? Because, sorry, one, because every vertex had degree 3, right? Every vertex has degree 3 in my graph G. And I'm removing exactly 2 degree from every vertex because I'm deleting these two edges. So this vertex must have only 1 degree left, which could be adjacent to anything, but I don't care about that. So this is a one regular graph, right? What do I mean by one regular? Every vertex has degree 1. So this G minus EC is a graph which is one regular. So this is fine. What do I mean by spanning graph? It means that every vertex is there, right? I mean, all the vertices, I'm not deleting any vertices, right? Basically, I am deleting only edges. So I have a graph with n vertices where each vertex has degree exactly 1. So how would the graph look like? It This is the only possibility it looks like this. So there are 1, 2 up to n by 2 vertices here, and let's say n by 2 plus 1 to n vertices here. So this is how the graph would look like, right? Is this clear to everyone why the graph G minus EC would look like this matching of n by 2 edges? So if this is clear, put plus 1. If not, you can take a time and ask me question. Okay, I'll wait for a minute because this is uh, not so easy to see, but not so hard. You can take a minute and think. Okay, I see three plus ones. For others, I hope this is clear. If not, please, you can ask me questions. Okay. Okay, I see enough plus ones. Okay. So, so this is clear. Now, if you see, all these edges are sort of isolated edges. They have nothing to do with each other. So I can always use the same color. I'll use a new color. First of all, I have used two colors for the edges which appear on the Hamiltonian cycle. So I have used two colors. So I'll use a third color and I will color the edges, like all the remaining edges, with the third color. There won't be any problem because these edges are independent in the sense that if you take two edges, they don't have any common endpoint, right? Because if you take the first and second edge, they don't have any common endpoint. So there is no problem. I can color all these edges with the same color. So how many colors we have used? Two for Hamiltonian cycle. I mean the edges that appear on Hamiltonian cycle. And if I remove those edges, I'm left with n by 2 edges and I'm using only one color for those n by 2 edges. So the answer is 3, right? Um, yes, right? Okay, okay. So, so if you have any doubt, you can ask a question. Meanwhile, I'll write the next question.
So the chromatic index is equal to 3, and the chromatic number is also 3 for cubic Hamiltonian graph, sir.
Uh, Let me think. What do you think? The chromatic number will be how much? Mm, let's see. I think it will be 3. Yeah. Yes, yes.
So for small graph, we can find it very easily.
Yeah,
But
I mean, there is a
as you have
so
generalized like this, you have generalizedly showing that how to remove the edges. But like that, can we say for chromatic number also?
uh
Uh, I think that in this case it will be dependent on the graph because say there is it will only be an even cycle, right?
mhm,
Now, if we go with the alternate red blue,
mhm.
now if there exists a what can I say an edge between the vertices which are both colored red,
Yes,
then it
yes.
will be three. Otherwise, if it is such that every vertex is related to the vertex where they are alternative, then it will require only two.
Wait, just a second. I think no, the answer is not even 3. I can give you an counter example where the chromatic number of a cubic Hamiltonian graph is 4. Can you see? Can you come up with a, so this is I think an easy example. Can you come up with a cubic Hamiltonian graph whose chromatic number is, let's say, 4?
A for
So so what is your example?
complete graph of 4 vertices.
Exactly, right? So if you look at K4, sorry, yes. So here, this is a cubic Hamiltonian graph. Cubic because every vertex has degree 3, and Hamiltonian because there's a Hamiltonian cycle. You can see this is a square. And here the number of colors required to color all the vertices is 4. So I don't think there is any good way to determine the exact chromatic number, I think it will depend on the graph, right?
Yes.
Yeah. Okay. So here is one more question on chrom. It's not chromatic number. Okay, yes, this is chromatic number. So question is this a true statement or false statement? Let me explain the problem. So you have a graph G, right? And it contains n vertices. And let's say the chromatic number of this graph is k. The minimum number of colors required to color all the vertices is k. Now, is it true that such a graph G will always contain at least k into k minus 1 by 2 edges? If you think this is true, prove it. If you think this is false, construct a counterexample.
K into K minus 1 divided by 2 edges.
Yes. So any graph with chromatic number k will all is it true that it will always contain at least k into k minus 1 by 2 edges? So this is not so easy to see, but I'll give you let's say 2 minutes. It's not that straightforward question, but not that hard also.
We can take a bipartite graph.
Uh, okay, so how many edges do you want me to take? So let's say
Mhm.
so bipartite
I
graph.
have taken K33.
So what is bipartite? So what is chi of G for bipartite graph?
Chi of G for 2.
2. Yes. So you want to construct a bipartite graph which contains less than, so how many edges? Less at
I
least.
have taken K33.
So this
Uh,
is K33. Okay. But the number of edges in K33 is
oh,
way more
sorry.
than K into K minus 1 by 2.
I
Then
just missed. I have. Uh,
yes, yes. It's okay. So again, take your time. I'll give you 2 more minutes. So the observation that you have, so I'll give you a hint. Okay. So the observation that you have to make here is the following. Um, so let's say you are coloring the
Chi
graph.
of, chi of G is definitely less than or equal to delta of G plus 1. Can we use that?
There is
Then we'll
no,
get. Uh,
So
that is true.
this is false statement for bipartite graph of like K22 if we take it is a false.
K22. Okay. Let me draw K22. Okay. So what is chi of G for this graph? 2. How many edges it contains? Is it 2 in, is it at least 2 into 2 minus 1 by 2? Yes, right? Because it contains one edge. So so this is not a correct counterexample because the chi of G is 2 and it contains at least 2 into 2 minus 1 by 2 edges. So this is not a counterexample. Yeah.
So this is a true statement. Then I have checked with 5 6 examples. Everywhere it is coming as
Yeah,
true.
so the answer is true. You are right. So the answer is true. But the interesting part is how do you show this for general K? So let me give you a hint. So this is interesting, and I'll let you think more. So the observation is that if you collect all the vertices which are colored with one color, then you collect all the vertices. So let's say you collect all the vertices colored with color 1, you collect all the vertices colored in color 2, colored 3, colored K, right? So let's say you collected all these vertices. Can there be an edge between two vertices in C1? Is it possible that there is an edge between two vertices in C1 or C2 or C3 or C4 or CK?
No, no.
No, right? Because it's a
Because
definition of
definition.
coloring. Yes. So there can't be edge clearly between the vertices inside one class. So this is what we call an independent set, right? Because all the vertices here cannot have any edge. So let's say this is C1, and then you will have C2, and then you will have this is outside. You will have like this. So let's say C2, C3, CK. You know at least K colors are required, right? Now, my question is it possible? So let's focus on only two sets for now. Okay. So let's focus on the vertices which are colored 1 and focus on the vertices which are colored 2. And for now, let's forget about the other vertices. Is it possible that there is no edge between these two? What if, my question is, what if there is no edge between a vertex in left side? So let's say this is left side and this is right side. What if there is no edge like this from left to right? Is it possible um, that there is no edge?
No.
Why not?
Then we can color them the same color if there is no edge.
Exactly, right. What he's saying is basically if you look at the vertices in C2 and simultaneously look at the vertices in C1, if there is no edge between C2 and C1, I can color C2 as C1 also, right? And color the entire set with one color. So I know that if I took vertices that are colored with color 1 and I put it in box 1, and let's say I took the vertices which are color 2 and I put it in, let's say, box 2, there must be at least one edge going from left to right, or the from C2 to C1. Can everyone see this? Why there should be an edge? If you can see this, put +1. If not, please ask me question. um, I see only few +1s. Okay, but I think right. So it's okay, let me just quickly explain again. So what I'm saying is this: you took a set of vertices which are colored with color 1 and put it in this part. So let's say this box, I mean, I'm just putting it on the right hand side, and you take all the vertices which are colored 2 and you put it on this side. And my question is, what if there is no edge between any vertex of C2 and any vertex of C1? What I can do in that case is change the color of C2 to C1, and there is no problem, because there is no edge inside C1, there is no edge inside C2, and if there is no edge crossing also, then I can just color every vertex as C1. There is no problem because there is no edge there. So I don't have any problem. So what I can see is the following, uh, that if you collect the classes of vertices colored with color 1, 2, 3 up to k, then between every two classes there should be at least one edge. Like if between C1 and C2 there should be at least one edge. Between C2 and C3 there should be at least one edge. So now can anyone tell me why there should be k into k minus 1 by 2 edges?
Yes, because it will become a connected graph.
Con-
Like if we take the classes,
Yeah, yeah.
every class.
Yeah, yeah.
Somehow n appears.
So
NPTEL
basically
minus 1.
I need to put at least one edge between Ci and Cj. So if you take a class Ci and if you take class Cj where I is not equal to j, so you take two distinct classes, then there is an edge. Now, in how many ways you can choose two classes out of k?
KC2.
Yes, k choose two, right? So okay, so okay, I think some of you may not be. So does everyone know what is k choose two, or is there anyone who doesn't know what do I mean by k choose two? Okay, I'll assume all of you know. So basically k choose 2 is basically k factorial divided by 2 factorial, k minus 2 factorial, and this is basically k into k minus 1 by 2. So you can simplify this and see this is not so hard. So basically I need an edge between every two classes, and there are total k classes. So out of k I have to choose two classes, so that there will be definitely an edge. So the number of ways I can choose two classes is k choose 2, and between every two classes there is an edge, so the number of edges must be at least k choose 2, and k choose 2 is basically exactly k into k minus 1 by 2, right? This is simple. So the only observation you need to make is that if I have a class colored with color 1, and if I have a class of vertices colored with color 2, at least one vertex of C1 should be adjacent to at least one vertex of C2, right? And the only question is how many classes are there. If there are k classes, the number of edges should be at least k into k minus 1 by 2, because you need to pick two classes, add an edge. You need to pick two classes, add an edge. So the question is how many ways I can choose two classes out of k, and the answer is k choose 2 or k into k minus 1 by 2. Both of the things are same. Okay, so the answer here is true. Okay. Okay, so I think we have done a lot of chromatic number, chromatic index. So let's do a question on planar graphs, right? So let me see the question. Okay. Okay, so here's a question. Is k phi a planar graph? So k phi is clear, right? K phi is a complete graph on five vertices. My question is that is it a planar graph?
No.
No. Why?
In planar graph, we are required to to represent it in a manner that no two edges cross each other, right? Basically, in a layman terms.
Yes.
Now, because uh, there are odd vertices, now if you want to connect, say, two alternate vertices, like uh, then you can go from one side, which would be fine. Uh,
Okay, so let's something like this. So I need
yes.
to
Now, if we connect the yes, now if we want to connect the the next vertex, like the next adjacent vertex to the
yeah, so you're right. So basically the problem is this edge, right?
yes.
Yeah, so basically, but see, so here is a problem. Uh, now when you are, I mean, when you are writing in the answer in exam, you cannot really say that there is no planar drawing, because the question you can always ask yourself is the following, that there are two possibilities. Either you are not able to find a planar drawing, or there is no planar drawing, and these two things are different. So here I'm not able to draw a planar graph which is k5. So here I'm not able to draw it, but does that really mean that there is no planar graph? I mean, here it is, you can sort of argue with these edges, but I need something that you have seen in class. So there is a necessary condition on the number of edges of the graph. Do you guys remember? Um, so the number of edges in my graph G is at most how much in terms of number of vertices? Does anyone remember this?
That 3v minus 6.
Yes, yes, exactly. So this is again, this is proved in class, so I'll not again prove it. So this is proved in class using Euler's identity or Euler's proposition, which is v minus e plus f equals to 2. So this is something we have seen in high school. I think, I hope all of you remember. This is something I think we have seen in 7 or 8 standard, that if you have a planar graph, v minus e plus f is equals to 2, or 10th standard. Anyways, so you can use this um, Euler's I don't know identity, and show that In a planar graph, the number of edges is always upper bounded by 3 into number of vertices minus 6. Right? This is a necessary condition. So if there is a graph and it is planar, then it must satisfy this condition. Now, if k phi is planar, then it should satisfy this condition. But how many edges are there inside k phi? Can anyone tell me? How many edges are there in k phi? How many edges are there in a complete graph with 5 vertices?
Nine.
9,
No, I think 10.
10.
10.
Right? Again, so yeah, so this is 10. So you should be able to do this because see, how do you construct a complete graph? You take 5 vertices and you make every pair of edges adjacent. So the number of edges inside k phi is equal to the pairs of vertices. How many pairs are there? There are 5 vertices. A pair is of 2 vertices. So 5 choose 2. So this is 5 choose 2, which is 5 factorial, 2 factorial, 3 factorial. This is 10. Or you can also use the handshaking lemma, which says that summation of degree of vertices is equal to 2 into number of edges. Right? So V belongs to V of G. So here I have 5 vertices and each has degree 4, right? If you have a complete graph on 5 vertices, that means a vertex is adjacent to every other vertex. There are 5. So 1, 2, 3, 4, 5. So every vertex is adjacent to 4. So the degree of every vertex is 4. So this is summation 4 V belongs to V of G to EG. And how many times 4 is repeating? 5 times because there are 5 vertices. So this is 4 into 5, 2 into E of G. So this is 4 into 5 by 2 E of G, and this is 10. Okay, so E of G is 10. Uh, okay, I hope this is clear. And how many vertices are there? 5, because this is a complete graph on 5 vertices. So if you see, K phi doesn't satisfy this inequality because that this would mean 10 is less than or equal to 3 into 5 minus 6. So I'm just plugging E of G is equals to 10 and V of G is equals to 5, right? So this would imply 15 minus 6, 10 is less than or equal to 9. But we, I hope all of you know that 10 is not less than or equal to 9. So this is wrong. So that would mean that this necessary condition is not satisfied. This therefore k phi is not planar, right? Is this clear? Okay, yes, 10. Uh, okay, if this is clear, put +1. If you have doubt, please ask me. Okay. Okay, so I'll let me give you now. Let's go back to the question that I said we'll go back to. So let me. Okay, so let me just do this question: is this graph planar? Right. So the question is that here is a graph G. I mean, here is a drawing of this graph G. Can you draw a planar representation of this graph, or can you prove that this is not a planar graph?
Sir, the inequality is not holding. It is not a planar.
Okay. So the question is, can you prove it?
So we have
Until by which you can make it homeomorphic to K5 edge subdivision. What we
Uh,
call.
okay.
so we can say that vertex is 10 and edges is 14. So now if we put that inequality, it is not satisfying.
Okay. So let's see. So, okay. So this is also necessary condition we should check whether this is true. E of g is at most 3 into V of g minus 6. So how many edges are there? So let me count. 1, 2, 9 on
15.
the
Wait.
outside plus 3, 12, 13, 14. So this is 14. How many vertices are there? 10, right? There are 10 vertices. Okay. Okay. So is this true? E of g is at most 3 into V of g minus 6.
It is not.
There's some noise. Okay, I think we are fine. Yes. So if you see, 14 is indeed less than or equal to 3 into 10 minus
From
6.
edges 15 then. Each is degree 3.
Wait, wait. Let me just say finish this part. So this is 24. So this is fine. So this necessary condition is satisfied, right? Because I need E of g to be at most 3 into V of g minus 6. V of g is 10. So the number of edges should be at most 24. But here this is at most 14, right? So this doesn't prove the graph is not planar. So somebody else was saying something. I forgot.
I was
Huh,
saying we can prove it
huh.
homeomorphic to K55 by edge contraction or
Okay.
like.
So okay. So okay. Okay. So I
I
should
was
ask
just
this.
thinking
Wait, wait.
whether we can actually do it or not.
Wait, wait. So first, okay. So he's talking about. So how many of you know what he just said? Age subdivision, homeomorphic graphs, age contraction. These terms. Is there anyone who doesn't know any of these terms? Please ask, because the answer is will use this terms. So okay, so how many of you know what is the age contraction? If you know what is the age contraction, put +1, and that's all we need. I don't think we will require any more notation. So let me just rub this. Uh, so my question is this: do you know what is age contraction? If you know, put +1. If you don't know, please ask. I'll wait for a minute to see. If you don't know, put -1. If you know, put +1. Okay. So two of you know what is age contraction. What about the rest of you? Okay, so some of you, so you can just quickly say this, right? So this will save us time. Okay, anyways, so what is age contraction? Okay, so uh, so let's say, let me give you an example. So let's say here is a graph G, right? Uh, so there are three operations that we should know. First is vertex deletion, second is age deletion, and third is age contraction. So let me explain this one by one. So let's say A, B, C, D, E, F. So vertex deletion, I hope you know. Let's delete vertex F. So the graph would look like this, right? So this is g minus f. So the graph would look like this. So you delete the vertex and you delete the adjacent edges, right? So vertex deletion is easy. So let me draw back the graph f. uh, okay, edge deletion, again simple, right? So you just remove the edge. So let's delete the edge bd, for example. So you just remove the edge bd, and this is what the graph would look like. So you just remove the edge. Okay, so let me take age deletion. Now the age contraction is a little bit interesting. So what you do is the following. um let me give you an example. So let's contract an age b comma c. Okay, so what does this, wait, there is some delay, I think. Yes, I think this is visible. uh So what does that mean when I say contract an edge b comma c? It means you take the vertex b and you take the vertex c and you overlap, right? So you will take this vertex b and vertex c and you overlap. So you will create a new vertex here. You will create a new vertex here, which is, let me call it b comma c. Okay, you can call it anything, x y z a b c d, anything, but let me call it b comma c to denote that this new vertex is formed by contraction of an edge, right? I'm contracting the edge b comma c. That means the two end points of that edge will now become just one vertex. So b comma c is one vertex. And then we take the old vertices. So I'll take a, d, e, and f. Now what about the edges? uh, if so, for example, there is an edge between df, so I'll put that. Ef, I'll put that. Now b comma c, if there is an edge from either b or c to a vertex, then I'll add an edge between b comma c vertex to that edge. So for example, b was adjacent to d, so I'll add that edge. I also know that C was adjacent to E, so I'll also add this edge, right? So the new vertex is B comma C. So if B was adjacent to something, B comma C is also adjacent to that. If C was adjacent to something in previous graph, C B comma C will adjacent to that. So these two edges are there, and then A is adjacent to both B and C, so there must be an edge. So this is an operation called edge contraction. So I have contracted the edge b comma c and turned the vertex b comma c into a single vertex, right? So this is called an edge contraction. uh, Now is it clear? If yes, put +1. If not, I'll give you one more example.
So it is clear, but why we do that? Why we do that?
Yes, it will come up. Why do we do that? uh, I'll explain it to in the minute, but let me just make sure that everyone understood what is edge contraction. Okay, let me see if there is any doubt. Okay, I don't see any questions. So let me explain why this is interesting. Uh, okay, so there is a theorem by, what is his name? Wait, I don't know how to pronounce his name. Kowalski or something. So what he proved is this. So this is a theorem given in class. Okay, I'm not just giving random theorem. So this is given in class, that a graph is planar if and only if you take this graph. So for example, if you take, let instead of giving a theorem, let me give you a working definition. If you take g, you can, okay, let me write properly. Let's take a graph g. A graph g is planar if and only if, using these three operations: vertex deletion, edge deletion, is planar if and only if, using these three operations, we cannot get k5 or k33. So this is a theorem. I'm just giving you a equivalent statement because there are a lot of terms: homeomorphic, edge subdivision, blah blah blah. but we don't need to know so many terms. So this is what that theorem is saying. Given a graph G, the graph is planar if and only if following statement is true. Using these three operations on graph, not once, you can use it as many times as you want. Vertex deletion, edge deletion, and edge contraction. You can use these three operations uh, in any order, any number of times. Uh, if you can obtain K5 or K33, then the graph is not planar. And if you cannot obtain K5 or K33 graph, then it is planar, right? So this is
Sir,
why
we have to use three operations together or one
no,
by
no, no.
one or
You can use any operations as many times as you want. If you don't want to use any operation, you can do that also. So these are three possible allowed operations. You can use all three. You can use two. You can use one. You can use some of them multiple times. You anything. I mean, anything is possible. You can use it again and again. If you don't want to, you just don't want. You can skip it. And it's not like there is a order, right? So you can do these operations in arbitrary order. But do if but if you can do these three operations on a graph G and construct K5 or K5 or K33, then the graph is not planar. And if this is not possible, then the graph is planar, right? So now question is, in this graph, so in this given graph, can you use three operations? Can you use these three operations and obtain K5 or K33, right? I hope the question is clear. So the answer is no. I have already told you at the beginning of class that this is not a planar graph. So the question is, can you run these three operations any way you want, any number of times you want, and obtain K5 or K33, right? So I'll give you a minute. We don't have much time, so I cannot give you a lot of time. So think, and I'll give you the solution in the last minute.
If we use edge contraction
Mhm,
on
mhm.
BD, uh,
Okay, so I'll put B comma D in a box.
and can you please show me the graph?
Yes. Let me draw it here small. So let's say B comma D in one box. After contracting edge, you will get a vertex BD. Okay. Okay, I think, sorry, it is already 7, so I cannot give you time, but let me explain how you can get K3 comma 3. Okay. So what I'll do is I'll contract edge AB and I will construct a new node called AB. Okay. So what I'm saying is you look at this graph, you look at A, B. Okay. Uh, Wait, let me use this notations that I have already prepared because otherwise it might be confusing. So let me say A, B, C, E, F, G, H, C, J. Okay. So let's contract the edge A comma B and construct vertex AB. Then contract the edge E comma F. So if you see EF is here, EF is here. Contract edge EF and also contract uh, edge C comma H. So let's do comma comma. Right. So I'm contracting three edges: AB, EF, and CH. So let me denote here. So I'm contracting this edge, I'm contracting this edge, and I'm contracting this edge. So I'm contracting these three edges. So now, like I said, what happens after edge contraction? You replace the vertex A and B by a new vertex AB, and then you have the vertex AB here, and then similarly vertex E comma F and vertex C comma H. Now let's put the rest of the vertices on the other side, which is G, J, and D. Okay. Now, uh, wait. I think this is still delayed. Uh, wait, wait. It will appear in a minute. I hope. Ah, yes, it is there. So what I did, con I I ran edge contraction three times on these three purple edges, and I obtained A comma B, E comma F, and C comma H. And then I kept the G, J, and D as it is. Now let's look at the edges. If you see, A was adjacent to D, so AB is adjacent to D, right? A was adjacent to D, so the newly formed vertex after edge contraction on edge A comma B will be adjacent to D. Okay. B was adjacent to J, so AB vertex will be adjacent to J, and A was adjacent to G. So if you see here, A was adjacent to D, so therefore I put edge A comma B and D. Then B was adjacent to J, so this edge. Here I added edge AB and J, and finally I'm adding AG. So there is an edge AG, so I need to add AG. Now similarly, E was adjacent to C. Wait, there is something wrong. E is adjacent to. Wait, I think I put C two times here. So I put C here again. Wait, let me think which one should I change. E should not be adjacent to D. So let me put here something else.
B is adjacent to C.
Wait, I have missed some letter. G, J, 2262, 2279. Okay, so let's say G, H, I, J, K, Z. I don't know. Let me put Z. Um, let me think. I think I made a mess. Which age I contracted? A, B, C, H, and EF. So let's do this symmetrically now. Uh, now I'll contract the age. Uh, which one should I contract? Wait, let me think. So I need to contract. The problem was with CH was contracted, and oh, sorry. The three edges that are contracted are the same: A, B, E, F, and CH. Sorry, there is no problem. Uh, AB is adjacent to D, J, and G because A is adjacent to D, uh, A is adjacent to G, and B is adjacent to Z. Okay, let's say I have deleted the vertex Z. So, like I said, I have how many operations? Three. You can delete vertices, delete edges, and edge contraction. So let's say delete Z. I run this operation also. Delete Z. So there is no Z. I'm only constructing this. Okay. Now let's see if we can get K3, 3. So E is adjacent to Z, E is adjacent to D. So I'll make EF adjacent to D. Um, F is adjacent to J. So I'll put that. And F is adjacent to G as well. So I'll put this. Right? Is this clear what I'm doing? Can you someone please confirm by putting +1, it is clear what I'm doing by these edges.
Yes, yes.
Huh. So, okay, let's see. So is there a edge between CH and G? So is there a edge between this vertex C comma H and G?
No, no.
Yes, yeah.
From G, it is yes, yes.
Yeah, because
It's
Z is
X as
adjacent to
adjacent G.
Yeah. So H here is adjacent to G, right? So basically this vertex CH will be adjacent to G. Now is CH adjacent to J? Yes, because C is adjacent to J here. So J, and is CH adjacent to D? Yes, because C is adjacent to D. So I can put CD as well. But I think there is delay. Huh, yes, now it is fine. So if you see, I was able to construct K3, 3 using only these three operations, which were vertex deletion, H deletion, and H contraction. And due to the theorem, uh, due to this theorem, again I think there's a delay. Um, wait, let me. Anyways, I have told you the theorem. G is planar. G is not planar. Let's say G is not planar if and only if using these three operations, vertex deletion, H deletion, and H contraction, you get K5 or K33. So here I was able to construct K3, 3 using only these three operations, which is vertex deletion, I deleted Z, H contraction, I contracted the edge, purple edges, and I didn't delete any edge which was not adjacent to Z, and I was able to construct K3, 3. So this implies that this is not a planar graph. So this is not a planar graph, right? Is that clear? If this is clear, put +1. If not, then please ask me questions.
Sir, this is clear, but why we have tried for K5?
Yes, so if you see K5 and K33 themselves are not planar graphs. This is proved in class, so you can check.
You have changed this graph to K33. That
Yes.
where you got this intuition? That is my question.
You mean how did I decided which edges to contract?
Yes, and then
Huh?
changing this graph to K33. Why not K55 we have tried, sir?
K Yeah, yes. So this is pure trial and error. Okay, there is I did try K5. Okay, when I was solving this question, I did try to construct K5 by using these three operations, and I couldn't do it. It's not like there is some way to determine immediately whether this
Sir,
is K.
that means we have to do trial and error. No? That is
Yeah,
good.
yeah, yes,
Okay.
yes, yes, yes. This is true. Given a graph using these three operations, can you construct K3, 3 or K5? This is pure trial and error. I don't think there is any algorithm or anything or any procedure that you can do particularly and see if you have to construct K5 or K3. This is pure trial and error. Yes, the I did try K5. I didn't get it. Then I realized it should be K3, 3, and I also tried to draw the planar presentation of this graph. I couldn't do it. Then I realized it shouldn't be planar. Then I tried to use these three operations and construct K5 or K33. I realized K5 is not possible, and I was able to construct K3, 3. There is no, I mean, this is just practice. You will get it. I mean, I think there is a question like this in your assignment also. I think week 8 assignment. So you can try and construct K5 or K33 there. Okay. Uh, okay, let me
Okay,
see
sir.
if there are any questions. No, okay. Okay, so that was the last question. So, okay, there is one thing. So, we will have last class, last tutorial on Wednesday. Okay, I don't know if you guys are informed already, but the next class will be on Wednesday, which is 20th March, 5 p.m. And this will be the last class. Okay, so
Sir, what we will do is that you please revise us because otherwise we will not get good marks in exam.
yeah, yes. So the entire goal of that class is to do revision. So
Yes, yes.
I'll try to, I mean, it's impossible to cover the entire course in 2 hours, but I'll do as much as possible.
Just you revise from first week to last week, and so that we can refresh our memories. That's all.
Yeah, I mean, yes, it is week 1 to week 8 is the entire course. So I'm saying I'll do as much as possible in 2 hours. But then,
Yes.
yeah. Okay. So, okay. So see you on Wednesday. Okay.
Thank
Bye.
you.